Hello everyone. So basically I saw this Eink screen a few months ago online on sale. So upon typing its model number in Google, I couldn't find anything, no resolutions or anything, or I don't even know where it came from. But it's just a weird shaped Eink screen, I guess. I found it's kind of interesting and rare to see such long bar type ink screen, and the price was kind of reasonable, so I bought two. The seller said he has specifications for it, and then after I got it, I asked the seller, "Hey, where is the specification? Can you send it?" And the seller was like, "Oh, actually, I don't have it." Without specification means I don't know the controller chip, I don't know the pinout. Obviously, I don't have any example code to begin with. We kind of need to reverse engineer everything, and I thought it would be interesting to put it into the video. So, okay, then how do I reverse engineer it? Basically, there are two things I need to know. One is the driver IC chip, another is the pinout. So let's start from the pinout. So obviously this is on an FPC cable. One of the good part about these FPC cables is, well, obviously the traces are very clearly visible. So if I just take a picture or I use a scanner to scan it, I will be able to just trace down the line and know how it's connected. Basically reverse engineer the schematics by just looking at it. So if I can know like how this chip is being connected on the glass substrate, and I know the pinout of these tiny chips, I can from here just follow the trace, go to here and know the pinout. Then how about on the glass? If I just look at the glass, I can see these traces. It will be kind of trivial to just trace through these glass wires, these ITO wires on the glass. I can know how it's connected. So it's finally about what's the pinout of this chip. Well, to know the pinout of this chip, if I can get the datasheet of this chip, then I know it. To get the datasheet, I kind of need to know the model number of that chip. So it's down to the problem of knowing the exact model number of this specific chip used here. One of the things I can do, if I know the pinout, is I can hook it up to a microcontroller. Then usually these chips, they will have an ID register. By reading the ID register, I get to know what the chip it is. But obviously I don't know the pinout here, so that doesn't work. Another way is, well, assuming it's a write-only channel that I couldn't really read anything, another possibility is I just brute force it. There is a finite number of Eink driver chips available on the market. If I just go and get every possible drivers, I just brute force it, try every one of them and see which one works, then, well, we have a winner. But that also doesn't work because I don't know the pinout. So what's left? Or is there any other way can we get the pinout without knowing the driver chip? Indeed, there is. One of the ways is just by guessing. This is possible in some cases. Let's say if the screen has only very limited or highly regular pinout, you can see on the ribbon cable. For example, you can clearly see there are 8 kind of signal pins followed by a ground pin, then several more signal pins. Then that could hint it's an 8-bit parallel bus, right? Or you see only there are about like 5 or 6 signal pins, then that's probably a SPI, right? And if you can limit the pin numbers down to a reasonable number, like 5 or 6 pins you need to guess, you can kind of also just brute force it, see which one works. I should say this method is still possible here, but I need to reverse engineer this FPC first before I can kind of make some observations to see like what each pin might be, then start guessing it. So this is still a possibility that I can take if I couldn't identify the chip, right? Another possibility, unfortunately doesn't apply here, is you can try to find other screens that share the same pinout. This is a very, very effective method, especially in E-inks. Because E-ink is one single company. It makes sense for them to produce different screens with the same pinout. So basically, pretty much every electronic shelf label screens, like those with 1.5 inch 2.1 inch, 2.9 inch, I believe also 4.2 inch, 5.8 inch, 7.5 inch even. They all use exactly the same pinout, 24 pins. So if you see an Eink screen that's 24 pins, it's very, very likely it's the same pinout. Similar things is happening with larger screens like 7.8 inch, 10.3 inch, some of the 8-inch screens, they all share the same pinout. This also applies in the LCD world as well, even though LCDs might be made by different manufacturers, but they kind of just copy the pinout of each other to be compatible for good reasons. But unfortunately, that doesn't apply here. I don't find any other similar screens with the same 25-pin connector, so that's not an option for me. Let's back to the problem of identifying this IC. So what else can I do? Well, I still have the option to brute force it, but not by connecting a microcontroller, but just looking at it. You see, this is just a bare die that's attached to the glass. If I want, I can measure the dimension of this chip fairly accurately, like down to 0.2 millimeters, say. So guess what? Different chips have different sizes. As I said before, there is finite number of Eink screen driver chips. If I just go through every one of them and check their size and find the one that match this size, then it's likely that is the one I'm looking for. That is what I'm going to do. I'm not going to measure it under the camera, but I've already done it. This is about 13 millimeters by 1 millimeter. And we're going to see if I can find any matching ones. So it looks like we have a winner here. It's the Ultra chip UC8176C chip, which in datasheet it says it has a dimension of roughly 13.1 millimeters by 1.03 millimeters, which is pretty close to our measurement. Another possibility is the SSD 1683 chip, which also is roughly on the order of this size based on the measurement. The datasheet of that chip doesn't specify the die size or any bump map, so we're going to focus on this thing because it gives us the full bump map or the pinout of the chip. So I made a scan of the backside of the screen so we can kind of zoom in and take a look. So we can see if it matches the chip that I identified before. One of the things we can kind of check quickly is the resolution. We can count the pixels, or another way is we can count these lines. So you see like the screen is like a 2D array. So we have X dimension driver lines and Y dimension driver lines, and we can clearly see these lines here. So these are the lines for the X dimension. These are for the Y dimension. We can see this is the first chip in the line and labeled as slave 3. Going down, we see the slave 2 where it only has X line because it doesn't have room to escape these Y lines. And then master chip also only has X drivers, and finally the slave chip, we see X lines and another few Y lines. So if we can count like X lines, Y lines, we know the resolution. This is zooming in onto the edge. So this is the Y driver lines. If I zoom in, I can start to see these individual lines, and so I can start counting. In fact, I've finished counting here, and I count in total of 80 pads on one side, so about 160 pads entirely. On the other edge also have pretty much similar sized numbered pads, so we're counting about 320 of these pads, so we know the vertical resolution of the chip is probably around 320. And then we focus on the middle part. Similarly, I counted these groups. I'm not entirely sure what they are, but each group is 4 pixels, so I can count in these groups. Entirely I count 100 groups, so it means there are 400 lines or 400 pixels. That kind of gives us the entire chip capability is around 400 by 320 pixels. And if we look at datasheet of this UC8176, it's 400 by 300. We're off by 20 here. We're gonna to see if this is really a mismatch, like if this is not the chip I'm looking for, or maybe some of these pads are not actually being used. So the real resolution is 300. This screen is definitely not making use of every possible pads. For example, here we see only about 120 pads are being connected. So it means the wide resolution using one chip is 120, and we see like two of the chip are connected, so it's 240. So that already gives us the full screen resolution 400, 400, 400, 400 on the x-axis, then 120, 120 on the y-axis. So the whole screen resolution is 1600 by 240. Now, on to answering the question of the discrepancies we saw before. Like we count there is 160 pads here, and then actually 161, and then the other side there is also 161. So it gives like a 322 total pixels that's possible on the y direction, but then this chip mentions it's only 300. If we actually take a look at the bump map, this is oriented in the same direction, we can actually see the pads from 282 to 287 is unused. The actual gate starts from the 288 and then continues to 437. Then a lot of unused pads again between the 437 and the 448. And if we go back to the photo we took before, we can actually see, yes, there are 6 unused pads clearly here. So it actually matches. We are expected to count more pads here than the supported maximum resolution. So now if we take more photos, probably like zoomed in area on these sides, and then referring to the datasheet, we should be able to, so if I take more photos around that edge and then correspond that to the datasheet, I should be able to derive the pinout. So yes, here it is. I have another photo taken on the other side of this this chip. I already labeled these, but I will show you how it's been done. This view is like this view 90 degrees rotated, so we know this pin is actually pin 1. So here we see pad 1 is no connect, which matches. I do see a pad here which isn't connect to anything. Then there is a lot of VCOM, which yes, there are a lot of VCOM that's shorted together because it's the same signal. And then a single VDM pin, yes, VDM pin check. A lot of VGL, a lot of VGL we see here. Then a single ground pin. So we also see this ground pin is connected later down there. We can see it's indeed the case. We got a bunch of VSL again, then a single ground, then VGH, so on and so forth. I'm not going to bore you with these details. I do see like some discrepancies here. These 2 pins are marked as ground, but on this actual screen, these 2 are fan out, not shorted to the rest of the ground. I will leave this as a question to be answered soon. So I also took another photo for like lower edge. Similarly, you can derive all these connections. This part contains all the important signals that will eventually trace them through to the ribbon connector. So back to the scan that I had before. This is backside, so if I do a front side scan as well, flip it and then also just overlap onto it like this, I can actually see the traces on the both sides very clearly and actually trace them down from the glass side, which we already reverse engineered, to the ribbon side. I already made some marks when I'm doing it. Also, like the question previously, I said like there are 2 pins that's supposed to be ground, but then on the glass it wasn't tied down to the ground, but rather like they were routed out. It's been answered here as well. So you see they are connected to different test pads. So the purpose is they're supposed to be ground, and they're grounded on the chip, so you can test if both are indeed connected to the ground. If not, there is something wrong with either your connection to the glass or the connection between the glass to the chip. And also there are these two pins are shorted directly on the glass. They are also connect to these two test pads so we can test. They are supposed to be connected. If you test they are not actually shorted, then it means there is something wrong with your ribbon cable to the glass connections. Then I open up a new KiCad sheet just to like draw the diagram while I was tracing these wires. Putting them all together, I got this Pinout that I can start writing software and connecting things up and see. So I have a very simple test program here just to see if it shows any signs of life. I have this initialize here and then a refresh. The initialize is also pretty short. It just configures all the pins, the spies, send a reset pulse, then it sets the panel to use the waveform from the OTP ROM. Then I set 0x04 to start up the power supply, then finally send a 0x12 to start the refresh. So if it's working, I should be able to see it starts refreshing the screen, like doing the black and white clearing sequence, and probably show some random data because I didn't send in anything. So I have the screen wired up to a Raspberry Pi Pico, and let's see how it works. Or see how it doesn't work. So was it really just nothing? Not actually. If we use a logic analyzer to see what's happening, I'm capturing the SPI bus and also the busy line to show if it's just trying to do anything. We can actually see yes. So we see the busy line first comes high, means it's not busy, then goes low again. Problem means the microcontroller has sent a reset pulse, so it's been under reset. Then it becomes high again, and we go into here. It's 0x04. Actually, we send the power on sequence, so it does. Yes, it does do the power on, and takes about 90 milliseconds for it to power on. In fact, this is a capture from not exactly the program I have show you before. I write more stuff to it, but it doesn't really change anything. But take a look at the end here. I sent an 0x12, ask it to start a refresh. It does seem to refresh. The issue is the refresh is only taking 3.4 milliseconds-ish. This is definitely not correct. Since I asked it to use the waveform from the OTP ROM, this tend to mean it doesn't have anything inside the OTP ROM. So the next step is manually load a LUT table, so it would probably do something. So if I try to use that, this is what I got. I didn't record it because I wasn't expecting it to work, so I have to show you some of the photos I take afterwards. This is showing what happens after I load a LUT or the waveform, and we can see it already starts to showing things. There are some kind of weird dots on the side and weird lines in the middle. One thing obviously I can do is using 0x00 and FF, alternating between that, and yes, I got full white and full black. That's looking good. And then I tried the classic 0x55 stripes. That's also looking good. This is definitely 0x55 stripes, so yes, that's pretty good. So that means I can move on to some image tests. And this is what I got when I'll try to display some text. So this is definitely not correct. There are some kind of reasonably garbled stuff on the side. If you look closely, it does kind of look like some text, but definitely not correct. It's kind of like missing every other lines, kind of, and also the middle parts, it's completely garbled. This pretty much tells me that 4 chips are not working in synchronize. And guess what? I never configured the synchronization register. That's probably the reason. So after configuring it, I'm getting this. So this is looking much better. I actually got text. But also notice like this is supposed to be on the upper left corner, but it's not. So this actually reveals a bug in my code where remember it has 4 different chips. Like this is the master chip, and we have slave 1, slave 2, and slave 3. In my code, for convenience, I just put master slave 1, slave 2, slave 3. So the display data between these two quarters are being exchanged or swapped. That's totally expected and that's easy to fix. So after fixing that, I can display some images. I'm not gonna to go into the details about how red works on these screens or how you can optimize it, how you can do different update modes. They are way outside the scope of this video. This video is really about reverse engineering it, which is really just tracing wires. Fortunately, it's kind of trivial. How to get these kind of like screens working. If you like this video, please let me know down in the comments. If you want to see some more of these screen reverse engineer videos or something else, please just let me know. And also, I have a Patreon page. If you would like to support me there, go ahead. It's also in the description. All the source code in this video is open source on the GitHub. You can check it out. So thanks for watching, and I will see you soon.